So that was reason number one why the bold signal is biased towards larger venules as compared to capillaries. But there's a second half to why the bold signal comes mainly from in and around venules as compared to in and around capillaries, and that is diffusion. So let me explain. This is the same graph that we saw earlier, and this is I took a slightly larger venule, but it doesn't matter. The idea is the same around capillaries. So we have our blood vessel, we have the warping in the field. So if you remember, the colors here are different magnetic fields. So for example, the gray magnetic field, let's just give it a name. Okay, let's say that this magnetic field in the gray shaded area is B0 prime. Whereas this kind of light gray, I guess, gray magnetic field, we're going to call this B second. And the white one, we're going to call this B third. It's just, I don't want to put a number, but this could be 3 Tesla, this could be 3 Tesla 0.00001, and this could be 3 Tesla 0.00002, something like that. Okay? But not to have to put numbers, I'm just going to say B0 prime, B0 second, B0 third. Okay. But for our purposes, these are strengths, are numbers that indicate the strength of the magnetic field. So now, let's say we have two protons. One is out here, and one is in here. At what radio frequency, what is the Larmor frequency of these two protons? Well, proton 1 out here is going at gyromagnetic constant over 2 pi times B0 first. So times whatever is the strength of the magnetic field here. How about this proton? Well, this proton is resonating at gyromagnetic constant over 2 pi times B0 third. So will these protons dephase fast or slow? Well, they are resonating at different Larmor frequencies, right? So one proton is gyromagnetic constant times, I don't know, 3 Tesla 0.0, and the other proton is resonating at gyromagnetic constant time 3 Tesla 0.002. So they are resonating at different Larmor frequencies. If two protons resonate at different frequencies, they will lose phase rather quickly, right? They will dephase, they will lose coherence rather quickly. Now let's see how diffusion affects this. Now diffusion just means that everything I've shown you so far, protons stay still where they are, but that's not what happens. Usually, you do radio frequency pulse, you put protons in a transversal plane, you stop the radio frequency pulse, and protons sort of relax back into B0. But the truth is that as they do this, protons actually move around. So as protons move around, they experience not just one magnetic field, B0, but they might experience more magnetic fields. For example, let's say that this proton right here, after a radio frequency pulse, because it's just moving around, does this, and sort of moves around in here. Now, and then once the proton reaches here, that's just when we take the picture. Okay, so we injected the radio frequency pulse, we stimulated protons. Between then and when we snap the picture, the proton number 1 moves from out here to in here. Okay. So over the whole period, what is the Larmor frequency of this proton? Well, let's make a couple assumptions. Let's just say that this proton spent 1/3 of the time out here, and exactly 1/3 of the time here, and exactly 1/3 of the time here, okay? Just to make it simple. This would mean that this proton resonated for 1/3 of the time at gyromagnetic constant over 2 pi times B0 first, out here. Then it resonated for 1/3 of the time at gyromagnetic constant over 2 pi times B second, in here. And then it resonated another third of the time at gyromagnetic constant over 2 pi times B third. So its Larmor frequency is the average of these 3 periods. Now let's assume that the other proton did exactly the same, but in reverse. So this proton started inside and now sort of floats outside. What would be the Larmor frequency over the whole period? So in fact, these two movements, you have to imagine that they happened at the same time. Okay, I'm breaking them down separately, but these two, one floated in and one floated out at exactly the same time. So one diffused inwards towards the blood vessel and towards the magnetic field, towards the warping, and the other one diffused out towards outside of the warping induced by the deoxyhemoglobin. So what would be the Larmor frequency over the whole period of this proton? Well, this proton spent 1/3 of the time at resonating at gyromagnetic constant over 2 pi times B0 third when it was in here. Then 1/3 of the time it did that inside B0 second when it was here. And then 1/3 of the time it resonated at gyromagnetic constant over 2 pi times B0 prime out here. So because of diffusion, two protons that would otherwise have resonated at completely different Larmor frequencies, this one and this one, actually, on average, went at the exact same Larmor frequency, which is what you're seeing down here. This is exactly the same as this. And we're just assuming that the order with which you transverse magnetic fields doesn't affect your actual Larmor frequency. Okay? So with no diffusion, these two protons, if one proton stays out here and one stays inside, they will dephase rather fast because they're going at different Larmor frequencies. But how about now that we added the diffusion to the equation? Would they dephase faster or slower compared to when there was no diffusion? They dephase slower because overall they're going exactly on average at the exact same Larmor frequency. So now these two protons are swinging together, are resonating for much longer before they lose phase. So adding diffusion, in a sense, it's as if it made the field a little smoother, makes everybody go a little more at the same Larmor frequency. Just by virtue of getting in and out of protons going in and out of the same magnetic fields and transversing these magnetic fields, some protons will actually resonate together for much longer, therefore will give a stronger signal. So let's see how this affects capillaries versus larger venules. Because see, with capillaries, so this is the image of a proton diffusing around the capillary. So a proton around the capillary can actually transverse many magnetic fields in between the radiofrequency pulse and TE when you snap the picture. So this particular proton experienced this magnetic field for a while, then this one, then this one, then this one here for longer, then this one, then this one, then this one, then that one, etc., etc. And you could imagine that there's another proton that is doing the exact opposite. And essentially, if you imagine that all protons up here went from here to there, just imagine that all the protons up here went from right to left, and all the protons down here went from left to right. They would be exactly equal to each other. So diffusion attenuates the effect of deoxyhemoglobin. Even though there is a lot of warping in the field, you can see it all here, because of diffusion, protons experience on average similar magnetic fields, and so resonate a little bit more together than they would without diffusion. So diffusion, in a sense, attenuates the effect of deoxyhemoglobin on the field. So would the signal be stronger or weaker with diffusion around the capillary? It'd be stronger, right? Just because of diffusion, the signal will be a little bit stronger in and around capillaries. How about venules? Well, around venules, capillaries, just because the magnetic field venules produce are so much larger with respect to just how much protons can diffuse. For example, protons in here, protons inside this magnetic field will never be able to escape it. And so this proton in here will never be able to go all the way out and change position with a proton that started here and came all the way in. Protons in here are stuck in here and will never be able to experience other magnetic fields. So diffusion doesn't affect much venules and doesn't affect venules to the same extent that it affects capillaries. So maybe if a proton happens to be on the border here, it might go out. And vice versa, a proton that is just out here might be able to diffuse in. But that's about it. All the other protons in here, they will not be able to escape and experience multiple magnetic fields, and therefore attenuate their differences with other protons. So around venules, diffusion does not affect much how quickly protons dephase. Around capillaries, diffusion affects very much the rates at which protons dephase because it makes them dephase slower. Around the larger venules, it does not. Diffusion doesn't play a significant effect. Let me show this in terms of this graph. So we were here. So at rest, we said this is the strength of the signal. Let's add diffusion to it now. Remember, diffusion almost makes the magnetic field a little smoother because protons experience multiple magnetic fields, and so they go a little bit more together. So will the signal be stronger or weaker? The signal will be stronger. So if you look at this red bar here, in fact, at rest with no task, the signal is stronger with diffusion than it would be with no diffusion. So the difference, the delta between off, rest, and task, active on, is very small. Now let's look at what happens around the venue. So we're right here, right? This is what happens. This is the strength of the signal with no diffusion. Let's add diffusion into the equation. Well, as I said, diffusion doesn't affect the signal, doesn't affect the dephasing of protons around venules much. So it's only a small change. It's only a small increase in the strength of the signal around venules. So this means that there still is a very large delta between when the participant is at rest and not engaged in any overt task, and when the participant suddenly engages in a mental activity and neurons sort of get excited and burst with activity. So, first, sorry, let me take one step back. So first, for starters, as this one is saying, the change between rest and active, between off and on around venules is just so much larger in magnitude than the change that we see around capillaries. On top of that, not only the change around capillaries is already small, diffusion makes it even smaller. So on top of the differences between changes in deoxygenated hemoglobin concentration, the difference between it being smaller in and around capillaries compared to in and around larger venules, on top of that, diffusion affects more the signal at rest in and around capillaries as compared to venules. So again, now there are two mechanisms by which just the signal, the change between when nothing particular is happening and suddenly a part of the brain bursting in neural activity, the change is just so much larger and so much more noticeable because of both these factors around venules than around capillaries. So overall, the type of bold sequences that we use, which are known as gradient recall echo, are just biased so much more towards larger venules than they are towards capillaries. So when you see an fMRI study, most of the signal people are looking at actually comes from inside and around larger venules as compared to capillaries. So this tells you something about the precision with which we can indicate which tiny piece of the brain it has an increased neural activity when we look at it with bold fMRI.